Hey, Jono, if you and Jonah are twins, then why are you a year behind on doing mechanics?
It's an interesting question, Kev. I saw the whole COVID thing coming, so I took the last year off to both indulge some other projects and make some money on the stock market.
Make money on the stock market, but it all crashed in March, didn't it? Most people who wrote it would have only just made their losses back by now.
Most people? That's the important bit there, Kev. You know me, and I'm about as far from most people as you can get, right? Stock market? It's really just about smart moves and good timing.
What, so this is another one of your jobs with the TARDIS?
Nah, this one predates the TARDIS, actually. Let me tell you the story. I ain't got rich parents, so paying the exorbitant uni fees is hard graft. I had the dough for my first year good to go, but studying under COVID was going to be awful, so I took what I saved and went fully high conviction with it. Single stock, maximum courage, no mucking around.
$40,500,000 all in.
Raise all in.
You had $40 million?
I wish. Nah, only about 10 grand, but that's still a decent bet.
And what did you put it on? Dogecoin?
Nah, Dogecoin? Dogecoin's peak, it's still in the future. I put it on Chegg.
Chegg? Seriously?
Yep, Chegg. So I bought in at 41 bucks a share at the end of January, pretty much as soon as I decided I was going to pull out for the year. And then I cashed out a few days before term one started this year. Sold at about 113 a share or so. Throw an exchange, walked away with 24 odd grand. That ought to see me a decent way through the old degree, I reckon.
Incredible. Most people would never expect Chegg to be profitable.
Nah, but the market it taps? So obvious. Yet, despite that, most universities and the fogies running them, they're so stuck in the past, I was a little surprised that the black market was going to catch them with their heads buried in the books. Some of them would have been surprised to even know that Chegg existed, let alone be on the New York Stock Exchange. Well, those old professors, nothing but dinosaurs in silly gowns and daggy clothes.
This lecture's on Hamiltonian mechanics, and so where I might start is just with a small piece of historical context. So you'll all be familiar with Newtonian mechanics, which is pretty much where you start in physics in high school or in first year, where really you're just dealing with Newton's second law for the most part, which is force equals mass times acceleration, or the other way of thinking about it is force is the time derivative of momentum. When Newton developed his theories for motion, he was also in parallel starting to develop the initial ideas of calculus. And one of the challenges there is that because you're developing the maths at the same time, the maths is often not well enough developed to give you a very well mathematically refined theory. And so the first thing that you get to when you come into a higher year mechanics course in physics is Lagrangian mechanics, and I always like to think of Lagrangian mechanics essentially as Newtonian mechanics with a calculus upgrade. Essentially you go 100 years forward in time, people have had time to work on the calculus that Newton started as part of working his way through trying to understand motion, developed a lot of the mathematics quite a bit further, and then you can start to put a proper mathematical framework around Newton's earlier ideas. And so you can see this in the form of the equations. For example, Euler-Lagrange equation pretty simply reduces back to essentially just Newton's second law. Okay, so where we're going to go in this lecture is to a third approach to mechanics, which is Hamiltonian mechanics. And again, this is something of a mathematical upgrade. All three of these versions, Hamiltonian Mechanics, Lagrangian Mechanics, and Newtonian Mechanics, are building on the same essential ideas. In Hamiltonian Mechanics, probably the big jump forward is that we go from a function called the Lagrangian, which doesn't have a really well-defined physical meaning, to a function called the Hamiltonian, which does have a very clearly well-defined physical meaning, which is that it is the total energy of the system. Okay, and all three of these things are equivalent. They're just different mathematical frameworks for doing the same types of problem. So before we get into Hamiltonian mechanics, let's just very quickly recap on Lagrangian mechanics, because we need this as a framework for where we're going forwards. Okay, so what we did was build a function called the Lagrangian, which is a function of a set of n generalized coordinates, which can be either translational coordinates or rotational coordinates, and their individual time derivatives, or what we call generalized velocities, and sometimes this thing is a function of the time as well. We build up this function called the Lagrangian essentially as the kinetic energy of the system minus the potential energy of the system. Okay, at this point it's just a mathematical function. The Lagrangian itself doesn't have a really well-defined physical meaning, but it works for the types of problems we do. What we then do is take that Lagrangian, take the derivatives of it with respect to the generalized coordinates q and the generalized velocities q dot, and then build together a set of n second-order differential equations that we call either Lagrange's equations or the Euler-Lagrange's equations that have a form a little bit like this. dl on dq is equal to d on dt of dl on dq dot. Okay, and I've put it in this form specifically because I want you to compare this to Newton's second law, right? Essentially what you have is a force is equal to the time derivative of a momentum. And in particular, we define a thing in Lagrangian mechanics called the generalized momentum, pi, which is simply this derivative of the Lagrangian with respect to the corresponding qi dot in that particular case, okay? And these momenta p we often call the canonical momentum or the momentum conjugate to qi. Okay, so every coordinate q will have a corresponding generalized or canonical momentum pi that connects to that. Okay, and the important thing in Lagrangian mechanics is, while we can think about this idea of having a generalized momentum, in the actual implementation of the theory, to go from the function Lagrangian to the equations of motion via the Lagrange equations, we never actually use that momentum. We're always working with q and q dots and not q's and p's. Okay, and this is the crucial thing that comes about when we get to Hamilton's approach. So let's take a quick look at the two key differences that we have in the Hamiltonian approach. There's two coming into the approach that are on this slide, and there's one that's an outcome that's not on this slide. I'll mention it very briefly, but it'll pop up again later and we'll see it. Okay, so the two differences are that we replace the function called the Lagrangian with a function called the Hamiltonian, and we define that Hamiltonian h via an expression here that is the sum of the products of the canonical momenta and the qi dots. Add all those together and subtract the Lagrangian off the end. This will seem like a completely arbitrary way to define the Hamiltonian in terms of the Lagrangian at this point, and that's perfectly okay. In 2 slides from now, what we'll do is implement a thing called a Legendre transform, which is really just a change of variables, and show you why it has this form, okay? But the important thing is we have a change in function from the Lagrangian to the Hamiltonian, and the nice thing about Hamiltonian, as I just mentioned, is that it has a physical meaning, and that physical meaning is that it's the total energy of the system. Okay. The other difference here is the coordinates, and this for me is probably the most important part of the difference in the Hamiltonian approach, because it's what drives difference number 1, as you'll see in a couple of slides. In Lagrangian mechanics, what we do is have 2 n coordinates, if we ignore the time, that are broken into 2 sets. One set is the generalized coordinates, or the positional coordinates for the system, q1 through to qn. And the other one is the time derivatives of those positional coordinates. In other words, all the generalized velocities of the system. Okay. In Hamiltonian mechanics, we keep the generalized coordinates, so all the positional coordinates stay exactly the same, but instead of using the time derivative of those, or the corresponding velocities, we use the corresponding canonical momenta. Now, at first sight, you might go, well, hang on, that's just a trivial thing, because all you do is you take the velocity q dot, multiply it by the mass, and you'll get p. That's not entirely true. If your generalized coordinate is a translational coordinate, then that's true. You can multiply the mass and you'll get a momentum. But if your generalized coordinate is a rotational coordinate, then actually the thing that gets you the corresponding momentum, which is an angular momentum, is the moment of inertia. And so to make a general theory here, you need to be careful about how you transfer from your q dots to your p's, because the transformation that you need to make depends on what that coordinate is. And for different systems, those different coordinates will have different meanings. Okay, so we need to be a little bit more careful about this. And this is why we'll take a somewhat careful approach to changing the variables between these two systems as part of our development for Hamiltonian approach. The other thing that comes out here is a difference in the outcome. You remember on the last slide, I talked about the fact that you get n second order differential equations as your equations of motion in the Lagrangian approach. In the Hamiltonian approach, you get 2n first order differential equations, right? So you get twice as many equations, but they're a little bit easier to work with because they're first order, not second order. And this is probably where you get your big power in the Hamiltonian approach. If you look in an undergraduate course, you're often dealing with very simple problems because you're trying to learn the technique. And one of the frustrating things when you first start out is you go, well, hang on a second, the Hamiltonian approach and the Lagrangian approach and the Newtonian approach, these new approaches don't get me much benefit over the Newtonian approach for these really simple problems. And that's absolutely true. The point where these methods come into their power is when you move to more difficult problems where you've either got more complex dynamical systems or a larger number of variables or both, and in particular in the cases where they're not analytically solvable. Then what happens is the Newtonian approach becomes a complete nightmare. The Lagrangian approach is a bit better, and particularly if you're dealing with harder computational problems, the Hamiltonian approach is even better because those first order differential equations are more stable to numerical and computational solutions. And so you basically find yourself with okay technique, good technique, special technique, and the advantages emerge as you increase the complexity of the system, working your way through. Okay? Now, coordinates is where I'm going to focus here, and before I get into showing you how you go from the Lagrange approach to the Hamiltonian approach in a formal way, I just want to make one really important distinction at this point, because we can make this distinction now, between something that we call state space and something that we call phase space. One thing that you'll notice if you're reading in textbooks and other people's lecture notes is often they can be quite sloppy about the difference between state space and phase space. Even if you go back in parts of my notes for this course, you'll find some points where I've actually called them the wrong thing if you're a real purist. But it's important to know which one's which, particularly if you get into more complicated dynamical systems work. So in both cases, whether it's Lagrangian mechanics or Hamiltonian mechanics, we have 2n coordinates, and we can treat that 2n coordinates as a 2n dimensional space. And so the state of the system at any one particular time will correspond to defined values of your q's and defined values of your q dots or your p's that specify in that 2n dimensional space one specific point. And then as the system evolves as a function of time, you'll get sort of trajectories in that space. And the trajectories in that space basically describe how that system evolves continuously as a function of time, subject to whatever physics you have going on in the problem. Okay. Now, that space has a different appearance between Lagrangian mechanics and Hamiltonian mechanics. And the reason for that difference is because you can't go directly from your QI dots to your P's via a direct transformation of just sticking the mass in, as I mentioned on the last slide, okay? So what that means is that if you've got a really simple system, which, you know, you've got 3 translational coordinates, then sure, your state space and your phase space are really just take your state space and multiply all your axes by m. But if you've got a system where you've got rotational coordinates in there, or significantly more complicated systems where not every axis scales that way, the state space of your Lagrangian system and the phase space of your Hamiltonian system will look very different, and you need to make that transformation between the two quite carefully via the Legendre transform, which I'll talk to you about on the next slide. Okay, so up until this point, they've really not made much difference, but this is the right point to actually point out that the spaces, the coordinate systems and the corresponding spaces for the Lagrangian approach and the Hamiltonian approach are very difficult, and if you're not aware of the fact that those two things are not the same thing, you can get yourself into trouble very quickly in sort of higher parts of mechanics going forward. Okay, so getting from the Lagrangian approach to the Hamiltonian approach formally is a thing that we call, is done by a thing that we call the Legendre transform. And what I'm going to do in this lecture is go through, and first I'm going to do in full abstract formality what a Legendre transform is. I'm then going to do a really simple little example just to give you some context to how this thing works. Then what we're going to do is take this and scale it up to actually taking the Lagrangian across to the Hamiltonian, so you can see the Legendre transform actually deployed in getting from one form to the other. And then what we'll do is we'll apply that transformation that we've done to a really simple problem in Hamiltonians, just to show you how it works there as well. So we'll kind of rip through this thing 4 times. Knowing how to do a Legendre transform is kind of useful, but it's kind of abstract here. And so I think it's more important, at least in terms of the context of this course, to understand how it's deployed to get you from one place to another than to be able to do it. But it's very useful to know because there are other parts of physics where it gets used, thermodynamics and so forth. And so later on, if you go along long enough in physics, you may be expected to actually do Legendre transforms for yourself of various different things. So it's actually useful to go through in this part of the course. All right, so we're going to go abstract here to start with. We're going to take our Lagrangian out and just replace it with some function, take our Hamiltonian out and replace it with some function. And those functions will be f and g. And you'll notice in the discussion that we had coming up to this that we had some set of variables that's common between the two functions. So if we think about Lagrangian and Hamiltonian, it's our generalized coordinates. They're the same for both. And there's some set of variables for the two functions that differ between the two functions. So in one case, we're looking at the generalized velocities for the Lagrangian, and we're looking at the generalized momenta for the Hamiltonian. Okay, so what we're going to do here as part of setting up our Legendre transform is we're going to take some function f, and that function will be of a set of variables u1 through to un, and another set of variables w1 through to wm, and I'm going to use m and n as distinct numbers here just to show you that they don't need to be the same lengths of set or same sizes of set. And what we're going to do is transfer to a new function that we'll call g that now has one set of variables v1 through to vn that is changed, and those v1 through to vn correspond to the u1 to un in the f, and a set of variables w1 through to wm that is common with the function f. Okay, so what we're really doing is taking our function f, taking some of the variables and doing a change of variable, and taking some of the variables and not doing a change of variable, and working out what that function that comes out the end is. Okay, just to put some names to these things, the set of variables that are going to stay the same between the two functions we're going to call passive variables, in the sense that they don't participate in the transformation. And the variables that switch from one to the other, we're going to call active variables because they're the ones that are changed. Okay, so to move forward on this, I'm going to need some whiteboards, so let's bring that up. And what we're going to do here is start with our function f of variables u1 through to un and w1 through to wm. And we're going to make a very specific change of variable here that is, this is ultimately the thing that gives the transformation we're doing here the name the Legendre transform. It's specifically what we're trying to do in this particular type of transformation. And that is to define our new variable v as the derivative of the function f with respect to the variable that we're trying to change. So in other words, df on dui. And we'll call this equation 1 now just to track it. Okay, so this is the key thing to the Legendre transform, is the relationship that we have between the variable that comes in, u, and the variable v that we want to get out, which is, the variable we want to get out, which is v. All right, now there's one really important thing in here, which is that we make an assumption for this to work. And that assumption is that our function f gives n independent v's coming out the end, okay? What we basically mean by this is that for every u that we put in the function f, when we switch to our function g, every variable v has a corresponding u, and they're all independent of one another. So to give you one example, if our function of u was equal to u, this would be bad because v would be df on du is equal to 1, and that means that every u would be equal to 1 and they're no longer independent. If we had f of u is equal to u squared, then this is actually good, because if we take the derivative, our v is equal to 2u, and so for every u there will be, every different u there will be a different v, and so we have independent variables in that particular case. Okay, so we're making that as an assumption here. Otherwise, we end up with a transformation that just collapses into a useless pile of maths. Okay, so what we're going to do is we're going to define our new function g here. And our new function g, I'm going to put brackets in here for the first time just so that everyone's clear on what's in the sum and what's not in the sum. And then after it, I'm going to drop the brackets so it looks like everything that's in the textbooks, okay? So this is sum over n I equals 1 of ui vi minus f u1 through to un, w1 through to wm, like so. Okay, let's call this equation 2 so we can keep track of it. At this point, this seems like a really arbitrary form, and it basically is. What will have happened here is that someone will have come through and played with this thing as a transformation and worked out that this thing works and it's kind of consistent. And at first, this would have started as just an interesting piece of pure maths, but then someone realized it's actually useful in various applications, like the one we have here of getting from a Lagrangian to a Hamiltonian, or like what you have in thermodynamics where you're converting between different variables in thermodynamics, and realized, hey, this is really useful, and this guy Legendre came up with this, so we'll call it Legendre transform and we'll just apply it. Okay, so at the moment this seems like an arbitrary function, and we'll play through the maths, and as long as the maths is rigorous, it's a sensible piece of maths, and then we'll see it generates us an interesting result that enables us to get from somewhere useful to somewhere more useful, and it becomes a thing that's sort of then accepted as part of physics, and we just continue using this thing. Okay. The key thing here is that this ends up being a mathematically rigorous approach on the way through. What we're setting out to do here is basically to write g as a function of v1 through to vn, sorry, put an n there, w1 through to wm in the end, right? So we're just trying to do a change of variable as part of this. Now, where the logical aspect of playing this game comes from is we need to consider an infinitesimal variation in G. Okay, this is quite a common approach when you're deriving things in physics. Change in G. Okay, and so we know from several variable calculus that we can basically write this thing quite straightforwardly as dg equals the sum I equals 1 to n of dg on dv I dvi plus the sum to m j equals 1 of dg on dwj dwj. Okay, most of you will be familiar with that in the context of, just imagine you've only got two variables, x and y. Your total derivative df would be your derivative along the x direction, so df on dx times dx, plus the derivative in the y direction, df on dy times dy, will get you df. And so what we're doing here is going from a two-dimensional space where there's two components to a 2n dimensional space, or here an n times m dimensional space, where we go, we have the sum of all the components in one of the variables and some of all the components in the other set of variables. Okay, so we're just breaking this up into our two sets, the active variables and the passive variables, combining all together to give you a total derivative in here. And what we're going to do is split these into two parts, A and B, which we handle separately at first just to keep track of what's going on. Okay, so let's deal with A first. A is the one that takes a little bit more work than the other one. And what we're going to do is start not with the whole term, but with just the derivative, partial derivative at the front. So what we've got is dg on dvi, and it's going to be, let's write this, d on dvi. We can bring in our term for g in here that we defined earlier, and I'm going to use the variable k just to distinguish the counting in here. So this is going to be k equals 1 to n of u k v k minus f u1 to un w1 to wm, like so. Okay, and so all I've really done here is just take my expression in number 2 for g and put it in so I can start taking the derivative. All right, so if we work through the steps here, what we're going to have is sum k equals 1 to n of duk on dvk vk plus sum n k equals 1 uk dvk on dvi. Okay, so let me just correct this label down here. That should be an I. And so these two terms come about because if I look at my first term just here, because it's a product, what I need to do is use the product rule. So it's the derivative of the first times the second plus the derivative of the second times the first. Okay? And then the term on the end, I actually need to use the chain rule for, because f is a function of u, and then I need to change from u to v. So this term on the end here will be minus df on dui on dvi, just by chain rule in here. Okay, I don't need to worry about terms in the sum there, because that term on the end is not part of the sum. The thing that you notice straight up is that duk on dvi and dvk on dvi will always be 0 if k is not equal to I, right? I'll let you confirm that one for yourself, but that makes the terms in the sum there collapse. And so this becomes dui on dvi vi plus ui dvi on dvi minus df on dui on dvi. Okay, so basically all the other terms in the sum collapse except for those two that remain. The one on the left we need to keep as a derivative that's not 0, but we don't know what it is. The one on the right we know is 1, right? dvi on dvi is 1. So we can pretty much straight write this up as dui on dvi vi plus ui minus df on dui on dvi. Okay, the next step in here is that we're still missing the little dvi that we just had up here. So let's bring that in. So we've got now dg on dvi dvi is going to be dui on dvi vi dvi plus ui dvi minus df on dui on dvi dvi. Okay, now there's one step that we can take in here straight up, which is that we know that dvi is equal to dvi and dui is equal to dui. And the reason we can do this is because these are underpinning coordinates for the functions. They're not functions themselves. Okay, so this is hopefully something you've learned in several variable calculus, that if you're dealing with functions of variables, then you have to distinguish between the total variable and the partial, the total derivative and the partial derivative. If you're dealing just with the coordinates, the partial derivative and the total derivative is kind of the same thing, like del v is dv. So where we end up with in this term now is this dvi down here kills that one up there. This dv here kills this one up here. And what we're left with is vi dui plus ui dvi minus df on dui dui, like so. Okay? And keep this term on the end as it is for the moment. And what you'll notice is if we go back up to our equation 1, what we did earlier was define vi as df on dui. And so this thing is just that, right? So we can take this line above, we go vi dui plus ui dvi minus vi dui, and you'll notice that the first term is now equal to the third term with a minus sign in front. So these two terms cancel out, and what we're left with here is ui dvi, like so. Fairly simple. Let's call this one equation 4. Okay, we've just basically cleaned up using what we know from several variable calculus. So the thing that we now need to deal with is b. And now we're going to go back and do exactly the same logic that we did, but we're going to apply it on this side. But it's going to play out a little bit differently now because we're dealing with the variables w instead of the variable set uv. So what we're going to have is dg on dwi, and it's going to be d on dwi sum k equals 1 n uk vk minus f of u1 through to un and w1 through to wm, like so. Okay, same as we did before. Now we can come down here and go sum n k equals 1 duk on d, let me just clean that up a little bit, duk on dwi vk plus sum k equals 1 to n of uk dvk on dwi minus, and this is the crucial point here, f is already a function of w, right? In the earlier one we had to use the chain rule because f was a function of u and we wanted to take the derivative with respect to v. Here f is a function of w and we want to take the derivative with respect to w. So this thing is really actually simple as df on dwi. Now these two terms here up the front, they actually knock out because now every single derivative duk on dwi or dvk on dwi is 0, because unlike before where we were relating u and v, and there's a relationship between those two variables because we're switching between them, our set w is distinct from both u and v because they're independent sets of variables compared to the function, okay? And so the derivative of these active set variables with respect to the passive set variables will always be zero. They're completely independent. So those two terms are 0, and what we're left with here is something really simple, which is just df on dwi. It collapses, just all folds out, gone. And so now the last step in here is to remember that we're just missing this dwj on the end here. And so if we bring this in, our variable's now in terms of indexed in I, so we should index it in I. And so what we'd be left with is dg on dwi would be minus df on dwi. And we can call this number 5 because this is another result that's useful to have. Okay. All right, so what we can do here now is take our result 4, which we got just up here, and we can take our result 5, which we just got, and we can put them back into 3. And just for context here, let me first write down what we had with 3. So we had dg is sum n I equals 1, dg on dvi dvi, plus sum m j equals 1, dg on dwj dwj. And if we pull in our two results that we had, what we'll get now is sum over n I equals 1 ui dvi. And just to explain why that sum survives, what we did up above, where was it? Up here, is when we dealt with a and b, all we did was take the thing from inside the sum out, right? So we got to keep that sum when we put it back together again. So now we're just inserting the pieces that we made in 4 and 5 back inside the sum. Minus sum m j equals 1 df on dw j dwj, okay? And so the interesting thing that you'll notice in here is we can say two things. First is that ui is equal to dg on dvi. So all we're really doing here is just going, this thing should be equal to this thing. Actually, that's not quite right. What we're saying is that this thing is equal to this thing. That's more right. And we also have in here that dg on dwi is equal to minus df on dwi. But we already sort of knew that from back up here somewhere, right? The really interesting thing to notice in here, though, is the symmetry. And to put this really explicitly, we've got ui is df on dvi, but you'll remember we started by defining vi as dg on dui. And so, hang on, let me just check I've got this right. No, I haven't got this right. Let me correct this. This is the G in here, and this will be the F just in here. That's better, right? Okay. So this was our definition that we had as number 1, and this was our equation that we got a little bit earlier as number 4. And you'll notice that there's a symmetry in here, right? One variable is defined as the derivative of a function with respect to the other variable, and vice versa, and the two functions switch in here, okay? And so we could use the same logic in reverse, just the same algebra that I just did, starting from the function g to get the function f, using the variables v to get u's, that would come down here and get us exactly the same answer, right? So the Legendre transform is kind of got a symmetric, like is a symmetric operation going from f to g or g to f with the two sets of variables. And so ultimately we can almost imagine that we've got an input system here and an output system where the variables coming in are u1 through to un. For some reason my brain keeps writing a 2 there, I don't know why. W1 through to Wm, like so. That goes to a V1 to Vn, W1 through to Wm, like so. We have some function here that's a function of our U1s to Un, just like that, see? I don't know why. Dodgy neuron. W1 through to Wm, and, oops, wrong bracket. Let's get that right. Like that. G on this side will be V1 through to Vn and W1 through to Wm, like so. And then we have almost a symmetric definition for our variables too. So on this side we've got Vi is equal to df on d ui. And on this side we've got ui is equal to dg on dvi. And then the way we define the function is symmetric as well, right? So here our g will be equal to sum n I equals 1 ui vi minus f, and here our f will be sum I equals 1 to n of ui vi minus g. Okay, and so if you do a Legendre transform and a Legendre transform, you get back to the thing that you had in the beginning. And if you just do it once, you go from a function and a set of variables to another function and a set of variables with some subset of those variables kept passive on the way across. Okay, really useful little piece of mathematics that we then apply to physics to get ourselves from one place to another, or one variable set to another that's convenient. And we do it again and again and again, which is why this is actually a really useful piece to have. Okay. I'm going to take a break in a moment. Before we do that, I just want to show you a really, really simple example of what this thing looks like with one variable, just to try and crystallize down what we did into something that's less abstract, right? So what we're going to do here is imagine some function of u and w. So we're just going to have one u and one w, keep it nice and simple. And we'll make this function something that's sort of arbitrary, like u squared plus w, something really simple, okay? Imagine we want to take a Legendre transform for this thing. What we're going to do first is we're going to define our variable v, and our variable v will just be, as we saw before, df on du. So this thing's going to be d on du of u squared plus w, which will just be 2u. And so what we're really saying here is that u is equal to a half v. Okay, we've got a relationship between our two variables now that's kind of simple. What we then want to do is get our function g, and our function g is going to be a function of the one variable v that corresponds to the active variable u, and our one passive variable w, which is coming through here just as a thing that comes along for the ride. So this thing, as we defined it earlier, is going to be the sum I equals 1 to n of u I v I f minus f of u and w. And of course, our index I is 1, and there's only one of them because we've got one variable in here. So this is really just going to become u v minus f of u and w in here, okay? If we start to substitute in our expression for u up here, this will now be a half v times v minus our function f of u, which we had up higher. So this will now be a half v squared minus, plus w inside here. And if we work this out, this will be a half v squared minus a quarter v squared minus w. If we work this out, this ends up being v squared on 4 minus w in here. And that's we've now done a Legendre transform from a set of variables u and w with a function f to a set of variables v and w, and we know the corresponding function g is now v squared over 4 minus w. Okay, so just to show you that we can actually transform, not just back again, but just repeat the transform and get back to where we started, what we would do now is we would go, well, we've got g of v and w, and it's v squared on 4 minus w. And so if we do a Legendre transform again, so now we define a new variable u as the derivative dg on dv. So our new variable u is going to be dg on dv. We're just repeating our Legendre transform for a second time. This will be d on dv of v squared on 4 minus w, which is just going to be 2v on 4, or v over 2. And of course, we can write this thing as v equals 2u. And then what we can do is define our new variable, our new function f of u and w as sum I equals 1 to n. Let me think through this for a second. My brain's gone blank. ui vi minus g of v and w. Okay, so all we've really done is just do the same thing, but now with a different function here. This will be u v minus g v and w, which will be u times 2u minus 2u squared on 4 minus w in this case. Let's just be really careful about that one. And so this thing will now be 2u squared minus 2u squared will be 4u over 4 is u squared plus w. And so this thing here will now be u squared plus w, and we've got our original f back, right? You'll notice, interestingly, that there's a sign change in our w that happens when we go from one to the next and then back again. So we go plus to minus, minus to plus, all right? You'll see that sign change pop through as we go. And what you'll notice, if you think about it now, is that sign change that you see on that last variable is where the sign change between the Lagrangian being t minus v and the Hamiltonian being t plus v, that change in sign comes from that change of sign you just saw there in the Legendre transform, okay? And in a sense, the Legendre transform is a little bit similar to the Fourier transform in the sense that if you take the Fourier transform of a Fourier transform, you get the thing back. And if you take the Legendre transform of a Legendre transform, you get the same thing back as well, okay? There's some interesting parallels between these two that I won't get into in this lecture, but I'll let you think about them because they're kind of interesting to realize as you come through as an undergraduate in physics. There's some nice tie-ins between these two things. So I think at this point we'll just take a quick break, and then what I'm going to do is come back and do a Legendre transform for the actual Lagrangian to show you that you get the Hamiltonian. And then after that we'll look at the physical significance of the Hamiltonian itself, just to confirm that it really is what we think it is. And then in a separate video I'll start to look at you know, what happens when you do Legendre transforms of real Lagrangians and how to use the Hamiltonian method and a few other bits and pieces. I'll see you in the next video.